Okay, in this video we're going to extend the principle that we talked about in the last video of magnetic field due to the presence of current. So the first thing we're going to do is take a long straight wire with a current in it. We'll face our current in the downward direction. And let's go ahead and put some numbers on this. I want to know what the magnetic field is going to be at a location over here 80 centimeters away from this wire. So if we have a distance of 80 centimeters away, and we have a current of 12 amps, I'm trying to draw this sideways here, then do we have enough information to figure out what the magnetic field is at this location? First of all, what's the direction? If we grab the wire and make sure our thumb is down, we should end up with magnetic field pointed out of the board everywhere on this side, and into the board everywhere on this side. Okay, so let's run our calculation. That gives us 3 times 10 to the negative 6 Tesla, 3 microtesla. And so far it's nothing new, it's everything that we've already done. But I want to connect this back to what we did in section 1 with the Lorentz force. Recall that if we have a wire in a magnetic field, that wire will experience a force. So let's go ahead and place a wire right at the point that we just calculated the magnetic field for. Also, we'll put a current in it so that it can experience a force. This one will have a current upward. And I'll give this one a value of 20 amps. Okay, so now we need to calculate the force that is exerted on this wire, as well as the direction. Notice that we used our second right-hand rule to find out what the direction of magnetic field was here. We will now have to use our first right-hand rule to figure out what the direction of the force is. So in our next step, we take the force per unit length. Truly, we're looking for force per unit length. We're not looking for force because we don't actually have a certain length of wire that we're interested in. So force per unit length is equal to IB sine theta. Remember, this is our second version of the Lorentz force law. What is theta? The direction between, or the angle between the direction of current and the magnetic field is 90 degrees. So as often happens, this will become, sine of 90 degrees will become 1. Okay, so our force per unit length is then going to be the current in this wire that is embedded in this field. So that's going to be 20 amps times the magnetic field that is produced by the other wire, which we've already calculated, 3 times 10 to the negative 6 Tesla. That force will be then 60 micronewtons. Per meter. Sorry. Okay, so we can look at this as an equation. Let's find that direction first. We know that we can use our Lorentz force first right-hand rule. So we point our finger in the upward direction. Middle finger should be pointed out of the page because our magnetic field is out of the page here. And then our other fingers will be this way, right? So that means that our thumb points like so, right? So our force is going to be in that direction. Current is this direction. B is out of the page, force is that direction. Okay, this means that the presence of this wire's current is causing this wire's current to experience an opposing force. If you use Newton's third law, you could see that the force that this wire experiences due to the presence of this wire should also be in that direction and should also be 60 micronewtons per meter. We can also use our right-hand rules to find that since the current in this wire is up, then we would expect the influence of its magnetic field, which is not going to be the same magnetic field, it's a separate magnetic field. That's going to have an outward direction in this region and an inward direction in this region. And so if we have a current going down within the magnetic field produced from the right-hand wire, then using our Lorentz force again, we would then have pointer finger down, middle finger is pointed out of the screen, and our thumb would point away, exactly as Newton's third law would predict. Let's take a look at the general equation here. If we were to erase all of these numbers, we would still be left with these two important equations here. Remember that the magnetic field is produced by one wire, and the force per unit length is what is experienced by the other wire. So this will always belong here, which means that the force per unit length on any set of wires will always be given as U0 times the first wire times the second wire, because that's where this comes in, divided by 2 pi times, and you could put r here, but really it's a little bit easier to distinguish this equation if you put distant d as a distance between these two. And again, there's no reason that I have to use d here and r here, but it just helps to kind of isolate them in your mind to kind of keep things organized. So this then is our equation for the force between two wires. You can work through the direction with your two right-hand rules to find out whether they're going to oppose or attract. As we saw before, if we have two wires with opposite currents, then we have a repulsive force between them. And if we have two wires with the same currents, then it turns out that they actually have an attractive force between them. If you can memorize that, great. I usually can't, so I just work through it in my head by using my right-hand rules. Either way. Okay, this is the force between two wires.